Hello all, my name is Vatan Sharma. I'm a senior geotechnical engineer in Midas IT. On the behalf of Midas IT, I welcome you all for this tunnel webinar series that is Advanced Numerical Modeling Techniques for Tunnel Analysis. So let's start the session today. Okay, so these are the contents of the webinar. First, we discuss the introduction. In the introduction, we will talk about NATM method and its philosophy. Next, we'll talk about the construction sequence. So the second topic of this webinar is rock mass support interaction, in which we talk about the support system, the rock mass support systems. And we also look into the most important terminologies of the tunnel, 2D tunnel especially, that is ground reaction curves, support reaction curves, longitudinal displacement profiles. In the third chapter, we'll discuss the tunnel design using Midas GTS NX software, in which we first talk about the ground reaction curve, the generation of ground reaction curve using Midas GTS NX. Then we'll move forward to the relaxation calculation, that is stress relaxation calculation for tunnels. Lastly, we have looked into the capacity curve generation with the tool we developed in Midas. And in this part, we also look into the demonstration of the model in the Midas GTS NX software. Lastly, we discuss the Midas GTS NX pricing that we have right now, the exclusive offer on the Midas GTS NX. So first we discuss NATM. So what is NATM? NATM is a new Austrian tunneling method, which we also call sequential excavation type method. Okay, according to the site condition or according to the rock type, we can go for the either full face excavation or the partial excavation. In partial excavation, there are also several types: heading, benching, invert, these kind of excavation, caverns, and lastly the partial excavation with site rifts. And can someone please confirm is my screen visible or not? Because some people are saying that it is not visible. Yeah, screen is visible. Thank you. So the next is this is the longitudinal section of this tunnel. You can see if I talk about there are so many drifts like A, B, C, D, E. So if I cut the section here, so these are the drifts. You can see the C drift is ahead of tunnel of drift D, and E is the behind the drift D. So this is how the tunnel excavation going on in the field. Now, NATM is based on the philosophy of build as you go approach with following cautions like your support has not too stiff, not too flexible. The installation of the support is not too early and it's not too late. If your support is provided too early, what's going on? If you provide support too early, which means you are not allowing the tunnel to relax a particular deformation or up to the certain extent. So you will get high stresses in your liners. If you provide supports too late, which means uh, you uh, which means you are providing extra relaxation to the tunnel, and there is the chance of collapse in the tunnel. The third is if your support is too stiff, so which again leads to the very less convergence to the tunnel, and you will get very high stresses in the tunnel lining, and there is a chance of like break in the tunnel lining or cracks in the tunnel lining. The fourth, if your support is too flexible, which means you are providing so much like deformations in the tunnel, and that is also leads to the collapse in the tunnel. So your tunnel lining should be optimum, which has a particular relaxation, a good relaxation, and the chances of collapse are also less. So you have to caution these four things when you are excavating the tunnel and when you are designing the tunnel. Now, this is the stepwise construction sequence. The first is the drill. First we drill the blast, then charge the blast, then take the blast. Then the process of mucking. Then the process of steel ribs. Install the steel lifts, wire mesh, and the shortcut application. Lastly, we provide the rock bolting. So this is the longitudinal section of the tunnel, and this is the cross section of the tunnel. Now, if you are going for the bench cut or invert excavation, so then you excavate the invert, then lastly you excavate the invert. The first thing you do for the final lining is the invert concrete, and then do the then we'll do the final lining in the concrete. Now we talk about the rock mass support interaction. The first is rock mass support system. This is a system of two components. The first is tunnel as a structure excavated in the rock and mass, and the second is the support system. So if you talk about some excavation, let's say the excavation is going on in some mountainous region and you have a very high cover. So it is not rock has to take its own load because there is no lining developed in the future, or you cannot support the lining. You cannot support the load with the 300 mm lining or the 400 mm lining if the entire load is coming on the lining. So the first thing, rock has to take its own load. The second is support system. So we additionally provide a support system for the plastic regions and all. So this is the, let's say this is the excavated periphery, and here we support the system. So the radial deformation going on, and we allow the tunnel to relax up to a certain limits. So these two systems are interdependent on each other. After that, when your radial deformation reaches to this point, the mechanical responses will occur. Now the load from the rock is transferred to the lining. Lastly, because of this load transfer to the lining, the pressure and the deformations will occur in the lining also. Now, the most important terminologies for the tunnel is like GRC, SRC, and in the next slide it is LDP. What is the meaning of GRC? GRC describes the relationship between the diminishing internal pressure and the deformation, which means, let's say you excavate the tunnel and total amount of internal pressure generated is 5,000 kPa. So until you are excavating the tunnel, the pressure is 5,000 until the deformation is 0. If the deformation is occurring, like you are providing certain relaxation, your internal pressure is decreasing according to the deformation. So initially it is in elastic region, but after a certain deformation or after a certain convergence, it is going to the plastic region. So this is the ground reaction curve. The second is the support capacity curve. The support capacity curve is defined as the relationship between the increasing pressure on the support. So let's say we install the support at 9 mm or 10 mm. When the radial deformations are 10 mm, after that, when the load is transferring from rock to support, so there is a certain point at which the deformation stops in the tunnel, and that is the equilibrium point. The third is longitudinal displacement profile. Longitudinal displacement profile relates the tunnel wall deformation to the location along the tunnel axis, that is behind the tunnel face and ahead the tunnel face. Let's say this is my tunnel face. So if I going towards the excavation or towards the rock, at certain point my deformations are 0. And if I go towards the excavation or back to the excavation, after certain length, my deformations are permanent. Okay, so that is UR infinite. Here the value is UR, which means you are 0 at the face and you are infinite at this point. And at this point it is 0. So it is somewhere between 0 to UR infinite. Okay, so according to this LDP and GRC, we have to generate or we have to calculate the relaxation value for the tunnel. because tunnel is a 3D problem and we are converting this 3D problem to the 2D problem. So we need some certain like relaxation in the tunnel so that my forces in the lining will automatically will less. Now, what is this three-dimensional condition? If I talk about this is the GRT. Okay, so in step one, we can see that this, if I cut the section at this axis, nothing is excavated. So my deformation at this point is zero and my internal pressure is highest. Okay, after certain excavation, that is after this excavation, let's say my point is reaches to the B or C points. This is GRT for the roof and this is GRT for the side walls. So let's say we are reaching somewhere here, and after that we install the support at this D displacement, and after that when I again excavate it, after a certain point my eye reaches to the E point, which means now if I excavate the tunnel further, there is no deformation is going on at this point. So this is the 3D condition of the tunnel, and now this condition has to simulate in 2D. So we have to calculate something so that this effect will consider in the 2D problem. So now we'll move for the tunnel design using GTS NX software. So the assumption taken in the 2D modeling today, like the geometry of the tunnel is same along a tunnel along a significant tunnel length, which is permit me to model the three-dimensional problem into the two-dimensional problem, that is the plane strain analysis. The second thing, the rock mass surrounding the tunnel I am considering is homogeneous, isotropic in all directions. The third thing, the structural elements, the primary lining is modeled as the elastic beam element in the plane strain model. So this is the problem statement. A modified horseshoe tunnel shape, which is of width and height approximately 12.9 to 10 meter respectively, and cover of the tunnel is 75 meter from the axis of tunnel from here, and GSI of the rock is 32 and MI of the rock is 7. The deformation modulus of the rock is 1200 MPa. The UCS value is 32 and the disturbance factor we are considering is 0. And we are also providing the lining support, which is of 250 mm shotcrete with a lattice girder 95, 20, 25. We will discuss it later. What is the meaning of this 95, 20, and 25? And the first thing we'll see in the model how to develop these ground reaction curve using Midas GTS NX. Okay. And after that, we'll do the relaxation calculations using these ground reaction curves and the plot using like Vacopoulos and Didrich equations. So with the help of these two plots, we will calculate the relaxation value. So now we are going towards the modeling part. So first, when we click on new, this window will open. Now, software asks you which type of analysis you want to perform. So because we are going for the 2D model, click on 2D. The default gravity direction for the 2D model is Y direction. Click OK. The grid size is right now the 20 meter. Now we can reduce the grid size here. Select 5 meter. Click apply. Now we have to create the modified horseshoe shaped tunnel. So for this, we already have tunnel cross section here. Click on create tunnel section. There we have several type of tunnel sections like 3 center circle, 3 center circle plus invert, 5 center circle and 5 center circle plus invert. So I am going with 3 center circle plus invert for this section. I am choosing R1 equals to 6.5 meter, R2 equals to 6 meter, and R3 equals to 15 meter. And the angle of this particular for this particular arc is 60 degrees and 55 degrees. By this option, you can also include the rock bolts. I'm considering rock bolts 11 for this for today's modeling, and the length of rock bolt each rock bolt is 4 meter. I click OK. So this section is directly created using the tunnel cross section, tunnel section option. Now we have to create the boundaries. So the tunnel access, the cover is about 75 meters. So we'll model 50 meter there, 50-meter height as a boundaries and will apply the load of 25 meter load of extra 25 meter. So click here. So because we already defined a grid of 5 meter, so if you check, so it is of 5 meter and the length from here to here is 50 meter. Now this section has a corner, sharp corners there, so there is a chance of high bending moment at this location. So what we can do, we can provide fillet here so that my bending moment will less when I am doing the analysis for this tunnel. So how can we provide fillet at in this section? Click on first intersect all these lines, click apply. Now break this line into two halves, click on break curve, select this line. The curve is of 50%, like 50% on this side and 50% on this side, click apply. So you can see this line is divided into the two parts. Now we can choose the option called fillet curve. Select these two edges, enter the radius 2 meter and apply it. So this is the fillet portion. Now do the same thing for the right portion. Select these two curves, enter, apply. So this is how you fillet the curves or fillet the corner portions. Now again do the intersection and click apply. Okay. Now now my entire section, or you can say the geometry, is ready. Now we have to create a mesh. So for the mesh, go to the mesh option. For the meshing, first we have to create the material, then we have to create the property. So for the material, click on material, click on create, click on isotropic, choose the rock type as a generalized hook brown, enter the elastic modulus because the problem, the elastic modulus is 1200 MPa, which means 1 into e to the power 5, 1.2 into e to the power 6 kPa. So this is 1200 MPa. The Poisson's ratio is 0.3. The unit weight of the rock is 26. And we are going for K naught, like K naught for the rock, we are going for 1. Now, click on the nonlinear tab, click on this 3 dots. Now here we have to define the nonlinear parameters for generalized Hook-Brown material model. So we are going with the MI value, that is intact rock parameter is 7, and the GSI is 32. The disturbance factor is 0. The UCS value for the rock is 32 MPa, so that is 32,000 kPa. The dilatancy angle we are taking 10. Name it as rock and click OK. So a material is added for the rock. Now we have to add the material for rock bolts and the line. So for the rock bolt, click on isotropic, check the structure option, go with the elastic material model. The elastic modulus is 2 into e to the power 8, that is 2 into 10 to the power 8 kPa. The Poisson's ratio is 0.2. The unit weight is 78.5. So this is for rock bolt. So name it as rock bolt and click OK. Now, because we are going for the lattice girder and the shotcrete both, so because we have to define it as a beam like element, So what we have to do, we have to find the equivalent parameter. So to find the equivalent parameter, we recently developed one tool. I'll show you. So this is the tool which is based on Caranja, Torus, and Dietrich, which we will also use for the plot of MN and QN curves. So click on OK. So I already have a saved file. I click on Open, go to the webinars, and so this is the JSON file. So I already go for the have this file in which all the inputs are defined. So for the shotcrete, first we have to define the material properties for the steel. So for the steel, the elastic modulus is 2 into 10 to the power 8, and the compressive strength is 435 MPa, that is 435 into 1000 kPa. The tensile strength is 435 MPa, so 435,000 kPa. And Poisson's ratio for the steel is 0.2. And we also using like 95, 90, 25, and 20. So what is the meaning of this lattice girder? So if you find any catalog on the Google, you can find that these type of numbers you will get, which means 95, 20, and 25. What is the meaning of 95, 20, and 25? 95 is the internal distance between the bigger bar or the top bar and the bottom bar. So 95 is the distance. 25 is the main bar S2, and 20 is the bottom bars, that is S3. So the total height of this entire lattice girder is H1 plus D1 plus D2. So which means it is 140. And the area you will easily get from the catalogs, which is 11.19 centimeters square. And the moment of inertia is 384 centimeter to power 4 for this is moment of inertia 384. So I directly use this height, this area, and this moment of inertia in the calculations. Now we have to add the shotcrete properties. So the elastic modulus for the shotcrete is 25,000 MPa, and the compressive strength is 20 MPa, so that is 20,000 kPa, and the tensile strength for that shotcrete is 2.5 MPa, so that is 2,500 kPa. The Poisson's ratio for the steel for the shotcrete is 0.5, and the shotcrete thickness is 0.25. The area is 0.25 into 1, because the width of the lining we are going for the 1, because the plane strength thickness is 1, and the steel so that is 0.25 into 1. The moment of inertia is BD cubed by 12. So B is 1, and this is D cubed by 12. So that is BD cubed by 12. And how we calculate this radius of the tunnel, I will discuss it later. So, and the factor of safety for which we will develop the MN curves is 1 and 1.5. So from there, what we have to do, we have to take the elastic modulus, the equivalent elastic modulus, and equivalent thickness. So we again go to the model here, click on create, again check the structure option, click on shotcrete, enter the elastic modulus here directly, and the Poisson's ratio is 0.15, and the unit weight is 25, and click OK. So the three materials are defined. This is the equivalent shotcrete material. OK, so you can name it as equivalent shotcrete also. Now what we have to do, we have to define the properties. For the properties, click on property. First we have to define the property for the ground. Click on create, click on 2D, click on plane, select the plane strain option, name it as rock, select the material type rock here, and apply it. Okay. Now click on create again, click on 1D, select the beam for the shotcrete. Now we have to define the section, name it as shotcrete, and select the material here, shotcrete, and the equivalent thickness is 0.248. So go to the section, click on section. The equivalent thickness is 0.248, and The width is 1 meter. So click on OK. So all the section properties are calculated by the software itself. Click OK. And we have to define the rock bolt also. So click on create, click on 1D, go with the truss option, name it as rock bolt, select the material type as a rock bolt, click on section, define a section. The section is solid round, select solid round, the diameter is 0.025. Click OK. Now click OK. So the three materials and three properties are defined now. Now go to the geometry, go to the size control. So I want finer mesh around here, like in this portion and around the rock bolt also. So select this, select these rock bolts and provide the size control of 0.5 meter mesh size here. Click apply. So you can see a size control, our software describes at 0.5 meter distance for entire rock bolt. Now go to the 2D automatic mesh, click on auto area, enter the mesh size 0.5. First select all the tunnel lines, name it as excavation and click apply. So you can see, or one thing I would like to show again, select auto again the area 0.5 excavation. You can also vary the element type here. Right now we have triangular, quadrilateral and triangular plus quadrilateral. So according to the modeling or according to the accuracies, you can go for the different type of element. So we are going with the triangular type of element, and you can also generate higher order mesh by checking this option. So we are going with the triangular mesh, click OK and click apply. So our triangular mesh is applied here, created here. Now select all the lines and enter the mesh size of 2.5 meter and name it as rock and click apply. So you can see a software automatically mesh and connect the mesh at the locations of the tunnel and even at the location of rock bolts. So what we have to do now, we have to mesh the rock bolt and the line. So you can hide the size control now. Now go to the extract option. First we'll mesh the rock bolts, select all the rock bolts and name it as rock bolt and click apply. So our rock bolt mesh is created. If you want to change the mesh color, because it's yellow on or both the meshes are yellow, so these are the rock bolt meshing. Now we have to mesh the beam element, or you can say the shotcrete. So click on extract option again, select the property type as a shotcrete, select all the outer lines of the tunnel and select the property type as shotcrete, select the shotcrete and click apply. So my meshing is done for all three parts, that is for ground, for excavation part, and for the lining and for the rock bolts. Now what we have to do, we have to provide the loading and the boundary conditions. So first we will provide the loading. So for the loading, go to the static and slope analysis. First click on self-weight. Because the default gravity direction for 2D is y, so enter gy equals to -1 and you can name it as self-weight and apply. Now the remaining load we have to apply as a pressure load, because right now the distance from here to here is approximately 50 meter and the tunnel is at the depth of 75 meter. So we have to apply the load for it. So click on the pressure load and select the line, the top face or top line of this model. The unit weight is 26 and the remaining overburden is 25. So 26 multiplied by 25 is 650 kilonewton. Name it as overburden load and click apply. Now, lastly, we have to provide the constraint. So click on constraint, go for the auto constraint, name it as ground boundary and apply. So a roller boundary on the wall is applied by the software and pinned boundaries at the bottom automatically. Now the entire modeling is done. What we have to do, we have to create a construction stage, because first we are going for the GRC development of the GRC curve. So click on stage set, click on add, double click on it, or you can change the name also. Like if you want to change the name it as GRC and modify it. Now double click on it. This type of window will open. So the first stage, check this show data to the activate. Nothing is activated right now. So the first stage is in situ stage, in which the excavation rock is there, the tunnel excavation is there, a rock is there, ground boundary is there, and the sulfate is there because it's an initial condition. And we did not want the deformation because of the sulfate of the ground. So we have to clear the displacement and click save. Now, then click on new. The next stage is overburden load. So activate this overburden load and again clear the displacement, because we are not interested in the displacement because of the load, because this is not an applied the surcharge load. This is the overburden load. So we have to click the clear displacement, save it. Now click on new. Now name the third stage as excavation, EXC. Now deactivate the excavation method. Now what we have to do, because we have to generate the LDP, the GRC curve. So for that we need deformation at each diminishing pressure. So for that, what we can do, click on LDF, click on LDF option, enter at 0 equals to 0.1, 0.1, 0.1. The third stage is 0.1, fourth stage is 0.1, fifth stage is 0.1, sixth stage is 0.1, seventh stage is 0.1, eighth stage is 0.1, ninth stage is 0.1. So the entire loading now is divided into the 10-10% loading. So 0 is the current stage, 1 is the first stage after the current stage. So this is like continuous. First stage after excavation, second stage after excavation, third stage after excavation. So in each excavation stage, we are applying 10% of the load. So click OK. You can name it as excavation 0 because it's the current stage. Save it. Now new, name it as 1, save stage. Nothing has to be activated because it's like a null stage, because 10% is load will automatically apply. Click on Sex 2, save it. Click on new 3, save it. Click on new again, 4, save it. Click on new, enter 5, save it. Click on new, enter 6, save it. Click on new, 7, save it. Click on new, 8, and save it. Click on new, enter 9, save it. So it's total 10 stage after 10 stage including the excavation. So this is the excavation stage and these are the 9 next stages. Now close it because we already create the construction stages. Now go to the analysis tab. Here your construction stage is saved from in situ to 9. Now click on analysis tab, click on general, select the solution type as a construction stage, name it as GRC, click on analysis control, activate initial stress stage for stress analysis because we are going with the K0 condition. So apply K0 condition, cut off effective pressure, and estimate initial configuration of activated nodes. In the nonlinear tab, I'm again distributing the load, the 10% load into the 5 increments. So I will get more number of points. So total 50 points will I get, the 50 points deformation will I get, and change the intermediate output to the every increment. You can also change the iterative scheme. Right now I'm going with the default iterative scheme. Click OK, click OK. Now we have to perform it using this option. Okay, when you click OK, software will perform this, the analysis and will give you the result. I already performed the model, analyzed the model. So this is the analyzed model, the same model. So the same construction stages and this same analysis case. Now we directly go for the results. So to generate the displacement, first we have to check the displacements. So this is the deformations, okay, for each stage. So to generate the GRC curve, click on extract option, okay. Select the displacement type because I am going to develop the GRC curve for the crown topmost part. So I'm going with the TY deformation because this is the TY deformation. Select the topmost point or the maximum point where you are getting the maximum deformation. Hide these in situ stages and these overburden stages up to 4 because we divide each stage into the 5 increments. Now go with the node/element type. Sorry, go with the step type and click table. So our table will generate, which means when the display there is no excavation, which means zero displacement. At first excavation, the excavation the 10% of 20% of 10%. So this is the deformation, 3 mm deformation up to the 20 mm deformation. So what you can do, you can copy these deformations, and I have this Excel. I will explain it to you and copy paste it here. Change scientific to number, and so these are my deformations: 0 mm, 0.3 mm up to the 20 mm. So these are the same deformation: 0 mm, 0.32 mm up to the 20 deformation. I only change the sign of the numbers. So at 0 mm, there is no reduction in the internal pressure. My internal pressure is in percentage. So this is 100%, 90%, at 98, at 2% reduction, the displacement is 0.32. At 4% reduction, the displacement is 0.63. Up to the full reduction, I am getting the displacement 20 mm. So when I plot these two curves like that, this is my GRC portion. This is my GRC. And you can see this part is the straight line. So this is the elastic region. The soil is or the rock is not in the plastic region up to this extent. And after this extent, you can see there is a parabolic curve. So there is a plastic deformations. Now, because to calculate, this is how you plot the GRCs, which I showed you in the PPT. Now, from the GRC and from this Bacapolus and Dietrich equations, we have to calculate the relaxation value for my model so that I will get the accurate forces in the lining, forces, bending moment, and the shear forces. So the tunnel is not circular. So to calculate the relaxation, I need four things. The first is RP, that is the plastic radius. The second is RT, that is the tunnel radius, and X is the face, that is the distance from the face, that is the round length. So X is the round length. This I have to assume. So I am assuming the round length of the each, or you can say the round length of each excavation is 1 meter, and I'm also applying the steel rib at each 1 meter. Okay, so this is U by Umax. This is ultimate displacement. Sorry, Umax is the ultimate displacement and U is the radial displacement. What is by ultimate displacement? Ultimate displacement is the 20 mm displacement which I am getting because of the relaxation. And I need one thing more, that is the plasticity. So how I check the plasticity in the model? So go to the last stage in the analyze model, click on this plane strain stress. This is the plasticity in the each model after the full relaxation. So it is somewhere around, if you calculate, somewhere 2.9 2 point something mm, that is 2.29 mm. Oh, sorry, 2.29 meter. So this is my plasticity. This is not plastic radius. So first we have to calculate the radius. So how we calculate the radius? There are two ways to calculate the radius which generally engineers adopt. The first is the equivalent radius. The second is the radius, the maximum dimension. So some engineer they calculate the area and they find the equivalent radius, equivalent circle radius. And some engineers they take the maximum dimension as a diameter and calculate radius accordingly. So today, in today's session, we are going with the equivalent radius. So to calculate the equivalent radius, first we need area. So how I calculate the area? Go to the model again, unlock the model. Okay, go to the in the worksheet, go to the model, go to the mesh tab, click on measure, select the excavation portion and calculate it. So if I change the unit here to the meters and again do it, select the object and calculate it, my area is about 104 meters square. So I take the area of 104 meter square and calculate the radius, that is 104 divided pi and root of 104 divided pi. So I get the radius of tunnel is 5.75 meter. Okay, how I calculate the plastic radius? The plasticity I assume the maximum plasticity is of 2.29 meter. So what I have done, I sum the this 2.29 and 5.75, which means RP equals to R plus plasticity. So that is 8.05 meter. My tunnel is tunnel radius is 5.75 meter. My round length is 1 meter. So if I calculate RP by RT, so it is 1.40. Okay. So we have to develop one line between 1 to 1.5, between here 1.4. And my X by R, X is the tunnel phase because I assume the round length of 1 meter, and R is, if I click on this, R is 5.75 meter. So the X by R value is 0.75. So this is 0.17, sorry. So this is 0.17 and this is 1.4. So I plot a vertical line at 0.17 until it touches the line of 1.4. Then I draw a horizontal line and I calculate U by Umax is 0.43. So which means U by Umax is 0.43. So if I change it to 0.043, now we have to multiply it 20 with, because my ultimate settlement is 20 mm. Now when I multiply it with 20 with 0.43, I get 8.612. So I get the radial displacement for which I have to apply the relaxation, that is 8.612. So I plot a vertical line in the GRC for 8.612 until it reaches to GRC curve, touches the GRC curve. Then I plot a horizontal line and I calculate that the diminishing pressure or the relaxation is 62%. So what we have to do, the relaxation, this is how we calculate the relaxation, the 62% relaxation. Now I again go to the model. Okay, I have to go to the again static and slope analysis, click on stage set. Now we have to create the another set for the design. So I name it as design, click on add, double click on it. So again this window will open. The first is in situ lining. First is the in situ stage. The same excavation rock is there, ground support is there, self weight is there, save it. Now, in the next stage, overburden, activate the overburden static load and save it and clear the displacement also. I forgot to clear the displacement in the first stage, clear the displacement in the in situ stage and clear the displacement in the overburden stage. Now again click on new, click on excavation, do the excavation, deactivate it. If you check the show data activate, you can see the excavation is done. Again click on LDF, click on LDF, delete this two stage. The distribution factor is 0.62 and 0.38, which means 62% relaxation and 38% load will taken up by the lining and the rock bolts. Click on OK, save it. Now click on new, go with the lining and activate the rock bolt and the shotcrete and save it. Now two sets are there. One is for the GRC and one is for the shotcrete and the lining. You can see design here. Okay. Now go to the analysis case. Click on general. Again select the solution type as a construction stage. Name it as tunnel design. Select the construction stage as a design. Go to the analysis control, check the same options which was done previously, click OK. Only in the output control, change the number of beam output to the 1 and click OK, click OK. Again, click on perform and analyze this tunnel design. When you analyze this tunnel design, I already have the model. Okay, so after the analysis, the model is logged like that, and these are the results. In the in situ stage, these are the deformations, these are the stresses, these are the x direction stress, y direction stress, and the z direction stress. And these are the stresses after the application of the overburden load. The stresses are increases. Now, after the excavation, the deformations are like that. This is the total deformations. These are the x directional deformations. If you want to check it in the change the here. These are the deformations before the excavation. Oh, sorry, before the application of the lining. After the application of the lining, these are the displacements x and y. So if you change it to the these are the x and y. So these are the displacement x direction and the y direction. Okay. Now these are, and the other things are the plasticity. If you want to check the plasticity, these are the plasticity, these are the major stresses, these are the minor stresses, and these are the beam element forces. This is the axial force after the application of relaxation. This is the shear force, and this is the bending moment. Now, how you developed the MN curves with the help of the tool and the GTS NX. So what you can do, click on extract again, select the result type as a beam element force, select the shotcrete lining, select the order type as a node/element, click on table. So you will get these forces here. What you can do, either you can copy paste it to the additional tool, or you can export the Excel also. So export the Excel. Let's say I'm saving on the desktop, that is 1, 2, 3, save it. Okay, so this is the 1, 2, 3, save. So these are the axial forces, bending moment, shear forces, and the bending moment. So copy these axial forces and paste it here, paste column. Now again, the one thing you have to think, like we export these. Okay, so we export these table as in kilonewton per mm. What we have to do, we have to change the units into kilonewton per meter. Again, go to the extract, click on beam element forces, select all, select go with the node and element. Again, select the shotcrete, change the unit to the kilonewton meter. And because we done all the inputting in kilonewton per meter, so we need forces also in the kilonewton per meter. Again, like export to the Excel, like let's say 235, and save it. So this is 235. Now copy paste these axial forces, paste it here, then copy these shear forces, again paste it here, and now copy these bending moments, paste it here. Click on get redistributed forces. What software do? Software redistribute the forces like for the steel and for the shotcrete. Now when you click on view curves, these type of curves will develop. So the section is passed for the shotcrete as well as my steel ribs are also passed. This is the MN curve, which means bending moment and the axial force curve for the shotcrete, and this is bending moment axial force curve for the steel. This is QN curve, shear force and the axial force for the steel, and this is the shear force and the axial force for the shotcrete. If you are then close it because you will get the forces. If you click on this generate report, this type of report will generate by this software or by the tool. So in which you get the steel input materials, what you input for the steels, what you input for the shotcrete, what are the section properties you are you choose, and what is the section properties for the shotcrete. These are the radius of the tunnel. These are the factor of safety for which you are getting the factor of safety. This is the equivalent thickness and equivalent elasticity modulus, and these are the curves. And you also get what are the input force you are getting from Midas GTS NX. Okay, so these are the input forces, and these are the redistributed forces for the shotcrete as well as the steel, either steel rib or lattice girder. It totally depend on the choosing of the section. So this is all from my side. If I go for the presentation again, if you have any questions, you can ask. We already discussed these deformations, like these are the vertical deformations, these are horizontal deformations. I already showed you the principal stresses. I already showed you the plasticity after the support applications. These are the axial forces. These are the bending moment, and these are the shear forces. These are the MN curves and QN curves developed by the tool. And this is the detailed MS Word report for the support capacity. Thanks for listening us again. Have a great day. Thank you. Bye-bye.